Right, good morning. So we're going to talk about how to do test of hypothesis, and more importantly, how do you tell which test of hypothesis you're supposed to be doing, and how do you kind of set this thing up? And like a lot of statistics, the math, even if you had to do it by hand, the math really isn't the hard part here. It's the English. It's figuring out what are they asking, and what are we trying to do with this. Okay. So going over, this is out of section 9.6 in your books for Navidi, and yeah, Navidi's 9.6 chapter. Um, but so in this problem, okay, we're talking about, okay, Census Bureau reported that the mean area of U.S. homes in 2015 was 2467 square feet. Assume a random sample of homes built in 2017 had a mean area of 2543 square feet with a standard deviation of 225 square feet. Assuming the population of areas is normally distributed, why did they have to tell us that? Okay, why was that sentence important? And the reason is because we need to know normally distributed here. Okay, that was terrible. Because the central limit theorem says we have to have at least 30, and we only have 20 homes here. Okay, so the reason why they have to tell us, hey, this is normally distributed, is because we have a small sample size. Okay, now they would do that regardless of what method we're using still. Okay, so we're going to go ahead, and that's an important piece, but that's going to add weight to our argument a little bit later. So we're not debating anything, we're not deciding anything just on these two facts, we're just noting it. Okay. Can you conclude that the mean area of homes built is greater than the homes in 2015? Use alpha equals 0.01. Okay, so what we're going to go back to is we're going to say, assume a simple random sample of 20 homes had a mean area. Well, what had a mean area? The sample had the mean area with a standard deviation. What standard deviation? The sample standard deviation. Okay, so because we have a small sample size that they told us was normally distributed, we need to know that. We're using a measurement. It's not a yes or no question. It's not, were they above this amount or were they below that amount? It was, here's the actual area that we had. Okay, they're not saying, you know, uh, 16 out of 50 homes had above this. They're not. They're measuring the square feet. So we're talking about the variable as a measurement. Okay, so that's telling me this is not a test of hypothesis dealing with proportions because we have a measurement involved, and there's nothing further in the problem that says, are they answering a yes or a no question here? Okay, we could turn it into one, but that's not what was presented. And because we're talking about assume that the sample had a mean area and a standard deviation, we're looking at, this is a sample standard deviation here, and this is a sample mean here. Okay, so when I'm looking at what kind of a problem this is going to be a t-test. We don't know what sigma is. We have a mu, we have a measurement, we have an average. Okay, and that's how we're going to go ahead and do this one. All right, so we have like 5 little steps of test of hypothesis, and again, the average is what they presented first. Okay, or what they presented as the standard. Okay, so we have a mean area of 2467. Okay, and it's come to my attention your book really likes to put the equality there. You should always put the equality there. Okay, the equality always goes with the HO because that's your tiebreaker. Okay, and they want to know, well, how do I know, is it right-handed or left-handed or what's going on here? They said, is it greater than the homes built? So when I'm looking at like my little chart here, right, my little normal distribution, they want to know, is it more than? Okay, so it's going to be a right-hand side, and I still want to know, is it greater than the 2467? Why 2467? Because that was the number that they gave me at the beginning. The X bar, right, we could go off to the side here. Let me go ahead and do my step 2 here. And alpha is equal to 0.01. And just off to the side, we're just going to write down the other stuff that they gave us. The X bar, right? What was the sample mean? The sample mean was this had a mean area of 2543. So this is 2543. we had a standard deviation. Notice I'm using S because it's the sample standard deviation of 225. Okay. Um, the years don't really matter, do they? I mean, that's, you know, that's important to the people that are building homes or buying homes, but we don't really care what the years was. That's not a number that's going to occur in our problem here. Okay, so we're going to go ahead and we're going to hit our test statistic here. And again, if this was an earlier time, this would be a little bit more involved here, but this is a calculator issue for us today. Again, we're going to go to stat. We're going to go to tests, and we're number 2. We're looking at a t-test here, okay? So we'll go ahead and give it the stats. We don't have any data to give it because even though they handed us 20 homes, they didn't go around and tell us, like, here were the square feet of those 20 homes, okay? So we're just going to go ahead and hit data, okay? And then we have what's our mu, right? What's our standard? What's our HO? And that was 2467. Okay, oops, we want stats. We don't want data. We want stats. All right, let's go back up here. Hit stats. All right, 2467. Okay, and then what was our X bar? X bar was 2543. Our S was 225. We still have to know how many there were because that's going to tell us how many degrees of freedom. The calculator is going to take care of, like, looking up the right t distribution for us, but they still have to know. And we want a right-hand side because we're looking at which is the greater part, okay? Oops, let's go ahead and make sure that that's selected. And then we're going to say calculate, all right? So notice mu greater than 2467. Well, here's our t, here's our p-value, okay? So our test statistic, what did we do? We did a t-test, right? We did a t-test. We said mu was equal to 2467. We said X bar was equal to 2543. We said our standard deviation was 225, and we said our N was equal to 20 here. Okay, so that's the pertinent information that we used for our t-test, and then we got our p-value. Okay, so the next step, okay, is to get your p-value. Again, this was this used to actually be 2 steps where this was a calculation we had to deal with, and then we had to look it up on a table. But our p-value is equal to 0.07. Okay. Now we're going to have to make our decision here. Okay, how does our p-value compare to our alpha? How is 0.7 comparing to 0.01? And p-value is quite a bit larger than 0.01, right? 0.07 is a bigger number than 0.01. You'd rather have 7 pennies than 1 penny. Okay, so since it didn't fall underneath the criteria here, okay, it wasn't more rare than we said was going to be acceptable, we say do not reject the null hypothesis. Okay, and again, this is a spot, if you're having trouble with this, this is a very typical, this is a very common error or a common problem for students to make is like, well, I've said don't reject it, and the idea is like, well, what does that mean? Okay, and your book kind of helps you guide through this thing, and the Connect Math, it does a lot of the, it puts a lot of the verbiage in for you. But we're not going to reject the HO. Well, what did HO say? It said the mu was equal to 2467. Oh, okay, we're good then. All right. So do not reject HO. And the Connect Math goes through and it gives you a very formal thing. It's like, we do not have evidence to suggest that the area is more than 2467. That's great if you can say it that way, and if that's comfortable language for you, fantastic. It's never been that comfortable for me. I appreciate a more casual style because it tells me that you understand what's going on with it, but the book will probably force you into a formal style. But you say, you know, the areas of houses hasn't increased. Okay. And again, we should say that more formally, but again, this is also, you know, Stats 101, and I don't want to trivialize that. We're learning a lot, and it's not easy. But I also don't want to overcomplicate the idea of what is this saying. Is it saying that it may have increased, right? I mean, it's possible, but we're not in our rejection region, so we're just not going to say, we're going to say, well, let's just go with, we don't have any of it. We don't have any reason to suggest that it actually got bigger. Okay, there's nothing here saying, well, no, it didn't. Okay, so that's how do you do a t-test, and that's how you diagnose. Like, how do I know it's a t-test? Let's look at another one. Okay, so this one says we have a random sample of 50 public school teachers in Georgia, had a mean average salary of 4830, okay, 48,300. So that was for the sample, right? The sample of the teachers had this salary. So when we're talking about this number here, you're going back to the sample. These 50 teachers had this average salary, okay? Say, assume the population standard deviation is sigma is equal to 8,000, okay? Notice they did not say anything about this is normally distributed. Why didn't they have to see that? Because by central limit theorem, right, this 50, this is a bigger number than 30. So we don't really care that it's normally distributed or not. We're guaranteed that this average is going to have a normal distribution because we have a sample size that's bigger than 30. So if they don't have to include that, we've got a big sample size, right? So they gave me the average for the sample, but they didn't say anything about the standard deviation. Now that doesn't mean anything specifically because they could have stuck it in another sentence. But they say assume the population standard deviation is this. Okay, so they're telling me, hey, this is sigma, all right? And honestly, for real life things, almost nobody ever knows the standard deviation. You almost always use a t-test in real life. But this is a textbook, and we're going to go ahead and assume that this is reality. Okay, and sometimes you do know, so it is important to know the difference, but more likely you won't. Okay, so can we conclude that the mean salary of public school teachers is different than the 50,000? Use alpha equals 0.01. So here, they're not saying, is it bigger or smaller? Okay, what are they asking me to compare this to, right? They're asking me to compare this salary to the 50,000. And really what we're trying to do is, are these different enough that I could really see a difference here, okay? I talk to people, I used to work at a convenience store, and we would label like a bag of chips like $2.99. And like, it's $3. People come in and they look at the $2.99, like, it's $2. Like, no, it's not. It's $3. That 1 penny is not enough to differentiate between the $2.99 and the $3 if you're clever, which is why the convenience stores label things that way, is because they want you to think, oh, it's $2. Okay, but there is a difference here. Well, so we're going to see, is it different then? So this is a 50,000 here. So yes, clearly it's probably lower. Okay, but we're just saying, is it different then? And remember, this is a two-sided test, so it's a little bit more robust than a one-sided test. So if you're on your own, you're like, I don't know what kind to use. You can probably get away with two-sided. If you want to be safe, use a two-sided test. Okay. Now, off to the side here, we're just going to write out, what else do we know? We still know that we had a random sample. We had n is equal to 50, right? And we had x bar is equal to 48,300. And the sigma, right, that was 8,000. So we'll just write that off to the side here. So this was my step 1. This is my step 2. My step 3 is we're going to calculate our test statistic, which is a z-test, because they told us this is the standard deviation, okay, population standard deviation. All right, so let's go ahead and pull this up. So calculator, we'll go to stat, okay, and we're going to go to test, and it's right number 1, z-test. This is how useful this one is, okay. And again, we just have the stats. They didn't feed us a bunch of numbers and make us figure out the mean. They did that for us. Thank you very much. I don't want to have to go through and calculate an average of 50 people. Okay, so we have 48,300. Okay, standard deviation. Notice they hand you sigma, right? It was S in the previous one, I think. 8,000. Okay, X bar. Oops, I messed up. H or the mu, oh, that's what you put in for your test of hypothesis. That was 50,000. Okay. The X bar, that was the 48,300. Okay, and then we have 50 people now. And then here, again, notice it's the first one. It's the most common one, is it's not equal to. Okay, so we'll go ahead and say it's different than, and then we'll go ahead and calculate this thing. Okay, so our z-test, what did we do here with the z-test? We said that mu o was equal to 50,000. We said x bar was equal to 48,000, and sigma was equal to 8k. Okay, so 48,300, right? 48.3 thousand. All right. Our p-value, all right, that's what we're getting off of here. Our p-value is 0.132, or 1.13. Let's go with 0.13. Okay, so again, we have to compare. We're going to say, well, how does our p-value compare with our alpha? Is 0.13 a bigger number or a smaller number than 0.01? Okay, clearly that's a much larger number. So again, right, that wasn't my intention, but again, we're going to say do not reject the null hypothesis. Okay, so what you're looking for is you set a criteria. You say if it's less likely than this 0.01, then something's up. Well, you found that the probability of getting a result like this was 13%. That's not less than 0.01, so it's entirely reasonable that you could collect 50 people that ended up with this salary, even though the average is a little bit higher. Okay, so do not reject HO. No evidence to suggest that the salary is lower. So, yeah, I'm pretty satisfied here that public school teachers still make an average of 50,000. Okay, so average of 50,000 a year. Okay, so that's, again, the important part here is diagnosing what's going on. And because they use this magic word population standard deviation here, I know it's a z-test because they handed me sigma. Okay, again, how do I know it's a z-test versus the proportions? Well, they didn't say, here's 50 school teachers and 14 or 28 of the 50 make above 50,000 and do it that way. They actually calculated out the salary. This is a measurement, okay? That's how they're treating it. Technically, I guess it's counted, you can count up the dollar bills, but they're treating this as a measurement. Okay. Next one. It's a general social survey asked 514 people whether or not they ever considered a career in science. 178 said that they had. So this one, we're not measuring anything. We're not saying how long did you study science, how much did you spend on your test, how many years of college did you have, how much research, how many hours of research did you do. They didn't ask any of that. They just said, have you ever considered it? And this is a yes or a no answer. 178 said that they had. Okay. Can you conclude that more than 30% of people have ever considered a career in science? Now, just because there's a percent doesn't mean it's always going to be a proportion. Okay, we could do a means test on proportions, but I think that's a little bit more rare and they try to stay away from that, but it is possible. So this 30% isn't evidence enough alone to say it's proportions. The fact that they're saying, can you conclude more than 30% of the people have considered a career? And all they gave me was 178 out of 514 people said yes. I'm going to go ahead and say this is going to be test of proportions. Okay, so we're going to go ahead and we're going to say this is a z-test. Sorry about that, z-test with proportions. Okay, so again, our HO, our HA, what are we comparing this to? Right? They don't have a historically, they just said, can you conclude more than 30 people had? I don't know where they plucked their 30% out of, but whatever. Okay, so we're going to say P0 is equal to 0.30. You have to change those percents into a decimal, otherwise it's not going to, you're going to get interesting results. They're not going to be right. Okay, and they wanted to, what did they want to know? Okay, can we conclude that more than? Okay, so again, we want the right side of the curve. We want the more than part. Okay, so again, if we were to look at, how proportion works, we want that stuff. okay, the right-hand side. Now, technically, we do have one more thing to check, okay? We want to make sure that we can actually use this technique, and I never give you a I would never give you a test of proportions that didn't satisfy the idea here, okay? But what we have to do is we have to say, is NP bigger than 10? And is N times 1 minus P, is that also bigger than 10? Okay, you don't have to show me that you did this, but you should be aware that this condition does exist, and there might be other stats classes where they spend more time on doing this. And it isn't always 10. In previous books, I used 5. So different books have different criteria, but your book says 10. Okay, so what we're going to do is we're going to say 0.30 times my n and 1 minus. So if something costs 30 cents, it never does, but just in case, you put down your dollar. How much change do you get for your 30 cents? Okay, and both of these are going to be bigger than 10. Okay, I mean, we could check, but I'll leave that how the math books say it. It's left as an exercise for the reader, okay, to make sure that this arithmetic turns out to be bigger than 10, bigger than 10. It does, okay. And I will never try to trick you that way with an exam question, okay. That's just unfair to do that to you. It's like, you know, I'm not going to squander one of my questions to say do this on on a question that isn't real, okay. So we've set up our step 1. We've declared our alpha. We're going to go ahead and calculate our test statistic. Okay. So we're going to say this is a, what are we going to say this is? We're going to say this is stat. How does your calculator use this? This is a 1 proportion z-test. Okay. So we're going to come over here. We're going to say a 1 proportion z-test. Okay. So we'll go ahead and click that on there. So, all right. So our P0, that was going to be 0.30. Okay. And then they said, well, how many people said yes? Okay. 178 people said yes, they considered a career in science. Out of how many? 514. So it's kind of nice that the calculator kind of does all of this for you. Okay. If it doesn't, I would just, and they said that your P hat, was, point 0.28 or something. Well, I would just say 28 over 100, or I would just say 0.28 times however many people I had and do it that way. I wouldn't try to mess with this too much. Don't make it harder than it has to be. And since they feed you the information that way, quite honestly, this is the favorite flavor I have for test of proportions. We'll go ahead and feed it to the calculator in the same way. Okay. And again, this is a one-sided test, right? They want greater than 30, so we're going to go with the greater than 30 and enter for that. And then we'll say calculate. Okay. So here are my p-value. Okay, my p-value is 0.011. Okay, that's close enough to 0.011. Proportions, let's finish writing this out. My p0 was 0.30. My x was 178, my n was 514, and we used the right-hand side there. Okay, so that was step 3. Step 4, okay, p-value versus alpha. Which one's bigger? We have 0.011 versus 0.05. Okay, so again, well, actually, this is different, right? We said the criteria is 5%. Well, this is 1%, right? We had a 1% chance of getting this result. And my criteria said, well, if it's less than 5%, it's not true. Okay. It's not by random chance, is what I should say. So because p-value is now smaller than alpha, which is different than the previous 2 examples, we say reject the null hypothesis. Okay. So what we're going to do is we're going to go off and we're going to say, can you conclude that more than 30 people have considered a career in science? Yes, we can. Okay. We can conclude that more than 30 people. So we have sufficient evidence to claim that more than 30 people have considered a career in science. So we're just going to say more than 30% have considered career insights. Do we please spell right correctly? Insights. Okay. And if you come over here and look, my P hat, this was the actual, which you would have gotten if you would take in your 178 divided by 514. The proportion you would get here is 0.346. So it's almost 35%. So we did a survey where almost 35% of the people said they considered a career in science, and we're saying did more than 30%. And that's a big enough that's a big enough difference to notice. So again, remember when they say this word significance, they mean noticeable. They don't mean important, they mean noticeable. Okay? So hopefully that shed a little bit of light on how do you pick out which kind of test of hypothesis you're going to do. Okay, because again, that is a bit of that's a tricky spot. Quite honestly, you could always look up in the corner because I think the way online exams go is they tell you where the thing is, and as long as you know what section it is, you can kind of double check yourself. But in a more wholesome environment, like if you were still doing this on paper, you would have to read this through for the clues and figure out which ones are going to work. But again, notice if I had said, right, what if I forgotten? I said, I don't know. Let's just guess. It's going to be this one. Well, what's my average? These are not averages. These are just numbers, right? They don't say sample average or anything like that, or the average was. What's my standard deviation? They didn't give me one. Don't try to force it. Don't be like Cinderella stepsisters and try to force your foot into the wrong size of a shoe. They didn't give us any of this information. Maybe I guessed wrong, right? That would be your first, rather than saying, well, the calculator must be wrong or the problem must not be giving you the right answer. Maybe it's possible that you picked the wrong kind of a problem, and maybe we could pick the other two to see if we get a better fit, right? You get that glass slipper and you're trying to do the stepsister thing, and it's not going to fit. Don't force it, right? You get all the right pieces, and they just kind of fall into place. And I'm pretty happy that, like, hey, that is reinforcing that I made the right decision for how to do all of this. Okay, so don't just look at this and say, well, I must be right. I'm going to force these numbers in. Like that ain't gonna work. Okay, so try to be careful about which one you're picking, and try to, like, I'm pretty sure it's this. Then you click that button and you say, how easy did the numbers fall into that subroutine to figure out which one is which. Okay, so with that, good luck, and I hope that all works out. So let me know if I can do any more, and best of luck with kind of figuring out which test of hypothesis is which. Okay, very good.